Oi, let's talk about cosmology. We have a horizon. Our universe's horizon is there because past that point we haven't received light of any kind. We have not received electromagnetic radiation. We haven't gotten any of that from past the horizon. But it's not as simple as that. If it was that simple, then a year's passing would be a light year's worth of more space that we could see. That's not the case because I explained that the universe is expanding in another video. What I mean by saying that the universe is expanding, space-time is expanding. I said at the end of the expanding universe video, space and time are like the same thing. They're connected. Time continues to go forward. You might say it continues to increase. The amount of time there has been increases. And if space and time are the same thing, then space is increasing too. Yeah. You remember the grid that I was talking about? The grid with the squares? Good, you do. It's like each square on the grid is getting bigger. It's still a square. And that means the expansion of the universe, and all those things that are redshifted, that isn't those things moving in relation to us so much as it's the space between us and other objects increasing. And the other weird thing is that because each square on the grid is doing this, that means that things that are further away from us are moving away faster, because you've got a square here that's growing, and then you've got the square next to it that's growing, and then you've got the other square on the end of which is one of our neighbors, and it's growing. So you have 3 growing squares worth of expansion. And so our horizon is close to the point where this expansion speed is about equal to the speed of light. It gets even more complicated because of relativity. Einstein's postulates of special relativity. Number 1. The laws of physics are the same for all observers moving at constant velocity. Okay. 2. The speed of light in vacuum is the same for all observers moving at a constant velocity. Did you catch that? The speed of light is always the same. How can the expansion of the universe keep light from reaching us by the universe expanding at the speed of light? Basically, light carries its energy in its wavelength, its frequency. The thing I showed you with radio and gamma waves. The shorter wavelength light has more energy, and longer wavelength light has less energy. Now, what happens with this expansion of the universe is that light expends its energy, its wavelength. Light is redshifted. Remember? Doppler shift? Light is redshifted by the expansion of the universe. And when the expansion of the universe is at the speed of light, light is redshifted so far that its wavelength is stretched to nothing. Judging by this, even if you think our horizon should be growing, even with special relativity and stretching wavelength, there's this other difficulty. It's not just that our horizon isn't growing, it's that our horizon is shrinking. Why is our horizon shrinking? I think our horizon is shrinking because the universe continues to expand. And the more the universe expands, the more speed of recession, which is the speed of things expanding away from each other. Space expanding things away from each other. I guess there's a difference. Our horizon is shrinking because things are expanding so quickly. The point at which light has no energy to reach us continues to be less and less. The point where apparently in 100 trillion years, expansion will reach the point where the last atom is ripped apart by the expansion of the universe. So that's our horizon. I think I was going to talk about the horizon in order to make it easier to talk about curvature of space-time, there's this equation. You know the Hubble telescope? It's named after a scientist who came up with a constant for the speed of recession, the expansion of the universe. So we can calculate based on how far something away. The simple version of Hubble's law is that the velocity at which an object is moving is equal to Hubble's constant, which is it's dependent on time. It's equal to Hubble's constant times the distance away the object is. With Hubble's law, there is the equation that I was talking about. It's an equation for how much stuff. Is stuff the scientific term? It's an equation for how much stuff there is in what we can observe of the universe. What we can see of the universe is finite. However, that's not the end of the universe. Partly because the standard cosmology appears to work for us, and the standard cosmology says the universe is infinite, and equations and stuff seem to work good with the universe being infinite. We can calculate it because of Hubble's law and Einstein's general relativity about gravity being an effect more than a force. I am exhausted, and it's overtime. So all the stuff I was talking about, all the hours of video recording I had, are to no avail, essentially. I can't finish the video about the curvature of space-time and what the universe looks like because I don't have enough time to edit. Fail.